Okay, so I'm going to take you through the Taylor rule, garch model and the vasicek model. We start with the Taylor rule. The Taylor rule was designed by John Taylor in 1983. He set out that the short-term target rate for interest should be dependent upon the rate of inflation and the growth gap. He divided the 1.5 weighting on inflation and a 0.5 weighting on the growth gap, as you can see in this formula here, and there's also a constant of 0.01, which is kind of like the long-term mean interest rate. So we've used the data, Fed funds data from 1958 to 2007. So first off, what we done was we ran a regression with the Fed funds rate as our dependent variable and inflation and growth gap as our independent variable, so that we could compare the coefficients of the estimation with the Taylor rule coefficients. So as you can see over here, we've done a table. So first off, we have the growth gap coefficient of 0.1423. So this is well below what Taylor suggests as the weight you should be putting on the growth gap of 0.5. If you look at inflation is 0.94. This is again well below the 1.5 suggestion of the weight by Taylor. So as you can see in the graph here, it's clearly evident that in a lot of periods you can see massive divergences in the Fed funds rate from the Taylor rule rate, such as this divergence here in the 1970s, and then you have in the early 1990s here, and then in the 2000s, the mid-2000s, which Taylor in 2007 paper points out to be a key contributor to the crisis and overheated the economy by fueling demand for loans. So what I done was here, I also took the two eras of Fed Reserve chairmen. So we have Alan Greenspan and Paul Volcker. Alan Greenspan was the chairman from 1987 to 2006. So we took that, we ran a regression on his era, on data for his era, and we found that the growth gap for his era was 0.45, which is close to the Taylor rule suggestion, and 1.53 for inflation, which is again close. So it shows that Greenspan kept monetary policy very tight, and you can see from the graph as well, during his tenure, the divergence is fairly small, apart from maybe two divergences. We've also done it for the Paul Volcker era. His era was he was brought in 1979 to deal with the stagflation crisis. So really, during his tenure, interest rates were always extremely high, as shown by the large value for the constant. So if he came in 1979, where interest rates were close to 10%, and they remained above, even about 6% was probably the smallest amount of interest, the smallest interest rate he set during his tenure. So the constant is extremely large, and this may have had an effect on the two coefficient values, which are very small compared to a Taylor rule suggestion. We also done the regression in OR, as you can see with the table here, and there's no differences at all really in the coefficients from Excel, so there's not much to talk about there. So we move on to garch. Garch is a measure of variance. So we took the prices from the S&P 500 from 2005 to 2008, and then we got the returns of these prices, and then what we done was we calculated the variance. Now, to calculate the variance in garch, the first selection would be the previous returns squared, but after that, what we do is we take the garch formula, which is omega plus beta times the previous variance plus alpha times the previous returns, as you can see in this in this formula bar up here. So then when you get these values, well obviously first off you have to put in estimates of the omega, beta and alpha coefficients, because you don't know them yet. So we put in values of 0.9 for beta, 0.001 for alpha and 0.08 for alpha. So then we use the formula to calculate the variance throughout the whole period, and then from this we get the log likelihoods. Then what we do is we sum the log likelihoods, and then with the sum of the log likelihoods we go into solver, and then we set the likelihood equal to its maximum value by changing the omega, beta and alpha cells. So what we got out of it was these values for omega, beta and alpha. So what can be noted here is really the important thing is that the values when alpha and beta are added together. So in this case the alpha and beta sum less to 1. If they were to sum above 1, it means that a shock would be permanent. But since they sum less to 1, a shock would decay over time, but it would be close to 1, so it's quite a persistent shock. You can see from the graphs here, so when you get the values for omega, alpha, beta, the variances change, so it allows you to get the graphs here. So we have a graph for the S&P variance throughout the whole period, but as you can see here with the financial crisis, there was a huge spike in the end, just at the end of 2008, which kind of disrupted the graph. So decided to draw a graph before that period, so as to give a better representation of the real variance over that period. We also calculate the long run variance, which is omega over 1 minus alpha minus beta. So that's about it. So we move on to the vasicek model. So this is a model that's designed to show mean reversion. So what I've got here is 1 month Fed funds rate data from 2001 to 2008. I would like to pick a bigger period, but the problem was the data wasn't really corresponding to the results here favourably. So I kept it to this period. So first off, what you do is you get the change in interest rates from the previous period, and then you put it in, you use this formula with, again, much like garch, you guesses for the A, the mean reverting speed, B, and the long-term mean and the volatility, and then you do it for every period, obviously putting in the current interest rate as you can see from the formula. And then what you do is you take the two previous cells, the results from the two previous cells away from each other, and then what you do is you get the probability density function, which is kind of like the height of a normal distribution curve. Then you log this answer, and what you do then, again the same as solver, you sum the logs of the probability density functions, and then you use solver to get the maximum value of this sum of logs of the probability density functions by changing the long-term mean reverting speed and volatility, and we got these answers out here, and this allowed us to draw this graph from I think it's this column, and what this shows here is that it's sort of reverting around a mean value. There is this kind of jump in 2004, and the interest rates remain quite high, but they do revert back down eventually. The data set isn't great, doesn't show it as well as it could, but anyways. So that's me finished.